Well, hello everyone. Thank you very much for being here. My name is Benedict Evans with Consumer Electronics Test and Development, as you can see behind me, and I'll be your host for this afternoon. I would like to offer a warm welcome to everyone here in attendance at this webinar, which is presented by none other than Matt Scholz from Radiant Vision Systems. Matt is the sales director of several core business units over at Radiant Vision Systems. He has over a decade of experience in metrology or measurement applications, especially when it comes to addressing the challenges in industries where absolute quality is of a critical nature. Currently, he oversees the development and implementation of automated visual inspection systems to aid manufacturers in ensuring performance and quality control for technologies that include displays, lighting, sensing, and illuminated components. Matt has been involved, as you can see, at all levels of the supply chain, all the way from the component to the integrator to the OEM, and he does strive to provide a consultative approach to help high-tech manufacturers reach their quality goals. I'm very shortly going to hand it over to Matt. Matt, thank you very much for being here, and also Julie for presenting with COVID, which is no easy task. So I'll hand it over to you now.
Thanks, Benedict. I appreciate it. And I appreciate everyone joining us today. Hopefully my voice stays intact as we go through this, as I am coming over COVID, but I'm really excited to talk to you guys about what we have to go through here today. So to introduce Radiant a little bit, for those who aren't aware, we specialize in imaging solutions, primarily imaging photometers and colorimeters, and we've been developing these systems for the past 30 years, specializing in high-resolution, versatile marketplaces where light and color are absolutely needed to be quantified at the R&D, QA, and the manufacturing process. We support our global customer base and our production lines all around the world, thanks to our direct offices that you can see in the US, in Asia, in Europe, and so on. We build more than thousands of systems every year to inspect millions of different devices, and our systems have been world-renowned and highly integrated by some of the biggest players in the consumer electronic industry. So for today's agenda, the things I'm going to cover are some of the basic aspects of display metrology and the traditional measurement equipment. We'll go through how a production demands are changing from now and what they look like into the future. We'll also look at the current inspection methods that stack up against display metrology and production goals. This will lead us into some of the common misconceptions that are being applied when you think about metrology systems in the production line and where their limitations normally lie. So things like capturing sufficient data, balancing speed and resolution of imaging systems, how to meet custom requirements, achieving automated inspection, and of course, connecting with the industrial systems. I'll address these concerns by introducing automated optical inspections, or what we commonly refer to as AOI, with the technology advantages for both metrology and production. Here we'll use some of the examples from Radiant's portfolio, and then I'll wrap up and look at what's available in the production measurement solutions today on the market. So to get started, it's an important baseline that we approach this from a scientific perspective. Historically, display metrology has allowed manufacturers to characterize displays with high accuracy for both R&D and quality control. During this section of the presentation, we'll take a look at the principles of display metrology, visual qualities of displays, and generally how we go about measuring them. Display quality is determined by different visual characteristics, and it really kind of depends on the technology we're looking at. But really common things are: how bright is the display? Is it producing the appropriate color? Does it meet gamma specifications, which is really a push that we see in the display industry to increase that gamut? What's the contrast ratio of the display? And we see this for all types of displays today. How uniform or bright are the colors across the display? Are there any generic defects or abnormal defects? Are there any unacceptable variations at different types of viewing angles, so different perspectives that someone may look at that display? And so much more. These are qualities that generally most display products have to validate at some point. And we use our sort of technology to go through the metrology analysis of these display and light emitting technologies. Like any science, both a standard and a reference guide display metrology. In this case, we apply standard principles outlined by CIE or international commissions on illumination. The CIE is an authority on light, and for nearly a century, they've provided methods of calculating light values based on a reference model. The reference model, of course, is human vision. The CIE's methods of quantifying measurements is derived from studies of visual response of a standard human observer. We calculate the perceived output of display based on the standard human eye response to the visible wavelengths of light. Our eyes are really sensitive to different wavelengths of light in terms of color and brightness. This sensitivity comes from the eye's cones. We have 3 types of cones in our eyes, each sensitive to a specific wavelength: long, medium, and short. The little graph in the lower right there is a rough illustration of the normalized response of each of our eye's cones. This shows how powerful we perceive each wavelength to be. The cones in our eyes can't detect individual wavelengths, unlike some of the systems that we're going to talk about today. They see the sum of the total light that all 3 of them are sensitive to. This is defined by the area under each of the curves in the graph. Understanding this visual response, which is called our spectral sensitivity, helps us understand our perception of brightness and color of various light sources, including displays. Here's a basic example. The large rainbow is a spectral power distribution of sunlight, which is its absolute power per wavelength. The curves represent what we actually see. If we want to measure how we perceive a display, so how bright is it, what color is it, we need to measure its light output using a method that derives values based on a model of our spectral sensitivity. We rely on 2 universal sciences of measurement to quantify our visual response, which are photometry and colorimetry. Photometry is the science of measuring light perceived by the human eye, and colorimetry is the science of measuring color perceived by the human eye. The standard bodies we mentioned previously, the CIE, provide methods for calculating the photometric and colorimetric measurements. Based on studies of standard human visual response, the CIE derived color matching functions, or the curves, one for each of the 3 values that are combined to create a perceived color similar to our eye's cones. These functions weight an output value of light and allow it to be measured in terms of human visual response at each respective wavelength. Because this method provides 3 values, one for each curve, outputs are commonly referred to as the tristimulus values. A combination of 3 X, Y, and Z tristimulus values are used to measure color. As we see the table, CIE provides formulas to calculate small x, little y using cap X, cap Y, cap Z in CIE. This measurement is chromaticity, and X and Y give us the chromaticity coordinates in CIE space. We map chromaticity coordinates on CIE space based on the chromaticity diagram you can see in this slide. This diagram is a 2D representation of the total perceived color space. Now, you may be familiar with these diagrams as a way of mapping various color gamuts as well. Here are some examples of color gamut, or the total producible colors by a device. The CIE chromaticity diagram was first standardized in 1931 and then adjusted again in 1976. Both diagrams are still used today. In the CIE 1931 chromaticity diagram, chromaticity coordinates are X and Y. And of course, in the CIE 1976 diagram, we're looking at U prime, V prime. Applying standard measurement principles is really important when we start getting into the quality control of applications. Colorimetry gives us the measurement tool that quantifies the value of what we're perceiving. For example, as a display manufacturer, I want my display to have a gamut that includes a specific color blue. Ensuring that my displays achieve this color blue ensures that my customers will have the intended visual experience. So if I want to know what this color is, colorimetry enables me to assign a numerical value to this color and set various types of pass-fail tolerances. The standard values that can be understood by everyone, we now have a common mathematical language that can be used to talk about each of these colors. Instead of telling my panel supplier, look at this blue. I need you to match this blue for all of the panels that you're going to manufacture. I could tell my supplier, I need the panels with a CIE chromaticity value of 0.1 in the X coordinate and 0.15 in the Y coordinate as an example. By creating bounding boxes and tolerance regions, I can help enforce the quality I want my suppliers to achieve. And with the right type of equipment, I can ensure that those thresholds are appropriately met, ensuring, of course, that the end product meets the expectations I have for my consumers. Luminance and chromaticity measurements are used in nearly all common display tests. Displays are expected to have uniform and consistent output, so we use comparisons of luminance and chromaticity values to show inconsistencies. As an example, uniformity, contrast, light leakage, Mura, and defect detections for pixels and line and particle defects are all really common things that most display providers are looking at. Other tests for particular applications may include things like image sticking, so that sort of image retention as there's that burn-in, maybe in an OLED technology or new display technology, viewing angle performance, how the display sort of reacts at different viewing perspectives, and of course the influence of sparkle. As we look at different types of technologies being used in different spaces, we know that ambient light becomes a strong component. So characterizing how much sparkle might appear on display thanks to an anti-reflective film or anti-glare film or coating is something that people are starting to care more and more about. So here are some examples. Contrast is measured as a ratio of the luminance between the dark and the light regions. Here we have an example of a checkerboard test image to perform this analysis. The concept is pretty straightforward. We measure the luminance of the white squares, and of course the dark squares, and we give a ratio between the two. We can also perform this test in different types of bright states of the display to help us truly understand the contrast ratio limits of the technology we're inspecting. Uniformity is described as the lateral variation in brightness and color values. So like contrast, we can measure uniformity by comparing measured values of luminance and chromaticity. In the example on this slide, we show uniformity analysis based on the ANSI brightness, which compares equally spaced points across the display. Discrepancies between each point allow us to determine if the uniformity falls within a specified tolerance. Defects in a display are typically random and vary in shape, size, and severity. So we can look at things like dots, whether there are stuck on, dead, or dim pixels, various types of contaminant, even dust or debris on the top of the cover glass. We can look at line defects, so connected or dead pixels, sections that are dim or overly bright, and of course, Mura, which is the unevenness or sort of cloudy effect that we see in displays where there tends to be a just noticeable difference in the display's emitting sections. Defects come in a variety of shapes and sizes. For example, each type of Mura has its own characteristics and requires a specific algorithm to detect, identify, and test. There are often several types of Mura present in a display, so it's helpful to analyze the software. It's helpful to have a software that can analyze the different types of defects in multiple ways, as you can see here in this slide. Here we show a few images with Mura analysis performed. In reality, there are many types of Mura that could be identified and analyzed across various types of displays. One way Mura is measured is according to the human visual perception, known as JND, so just noticeable difference. And it provides a model of standard human sensitivity to contrast. Applying JND, we can detect Mura regardless of where it occurs across the display and classify the type of Mura based on size, shape, and location. JND also allows us to grade Mura severity and create pass-fail scenarios based on the display and whether they exhibit the type of Mura that is either acceptable or not acceptable at the end-of-line process. New displays are relying more and more on emissive technologies where each subpixel in the display produces light independently. These displays include LED, OLED, micro-LED, mini-LED, and many others. In these cases, uniformity issues could be a result of discrepancies in output at the subpixel level. Many manufacturers of emissive displays want to measure individual subpixels to determine the exact difference in output from pixel to pixel, so these differences can be adjusted. The process of correcting emissive pixel output to produce a uniform display is called demura. That is, removing the non-uniformity from the display itself. To perform DMURA, a robust pixel-level measurement method is needed to accurately obtain the luminance and the chromaticity within the area of the individual subpixel. View angle measurements show us how brightness, color, and contrast vary as our eyes perceive the display at various angles. This is an important characteristic to measure in large and fixed display positions, where the display angle itself is not easily adjusted for the position of the respective viewer. For instance, we can think about TVs, monitors, or integrated displays in something like an automotive dashboard. Measuring view angle is traditionally done in the same way that we view the display, by measuring the display quality at each angle. All display measurements were generally first addressed with a lab-based system. The traditional display metrology system, which is a scientific instrument that was generally designed for spaces where measurement and time and space were fairly flexible, to be honest. Data was important. Without accurate data, we couldn't really understand the display qualities or how to adjust display properties for improvement for R&D applications. With data out of focus, the pros of a lab system are obvious. They're exactly highly accurate in terms of CIE measurement and luminance chromaticity, being able to do whatever we basically need to do to capture the most amount of data possible. For imaging systems, this means using the highest imaging resolution, regardless of how much data we may need to process. We also capture every point of data in extreme detail. Whatever data is needed, we take the time to measure it, from a single image of a display to the rotations for multiple measurements. However, these advantages for the lab have disadvantages elsewhere. Lab systems are relatively slow, both in terms of capturing and processing data. They can be large and bulky, including rotational equipment, large lab spaces, and so on. These systems often have limited automation, and this is because display quality is analyzed discreetly and in detail. It's also because really the necessary suite of tests for quality control is being defined on the fly, or sometimes being changed at an end-of-line perspective. The diagnostics phase of a lab measurement is typically not used for testing multiple parameters in rapid sequence. For similar reasons, these systems are often not designed with much integration capability in terms of communication of programming to plug into a larger fixture of automation. Now, this is how people traditionally think of lab-based systems. The original system designed for light and color measurement was a meter that relied on measurement of a single spot of a display at a time. A classic example of this is a spectroradiometer, something that is still widely used, of course, in the industry today. The instrument is extremely accurate. It captures very narrow sample of light and uses internal components to split it into its unique wavelength so we can calculate precise power per wavelength. A spot meter can be used for brightness, color, contrast, and uniformity of measurements. Although these systems are applied in production applications, they have the classic disadvantage of traditional metrology systems. If only one spot on a display could be measured at a time, we need to think about how many spots we need to capture, the positioning of the meter, the appropriate location several times for each display, the added cost of the robotics and communication. This is a time-consuming and possibly hard to make repeatable issue that induces additional error. We also aren't getting the complete picture of the data output from display at once, so the instrument is limited to what other measurements or aspects could be detected for defect detection. For defects like MURA, lines, dead pixels, originally there was no better method than human inspection. And still, in some places around the world, we see human inspection being utilized, but people are starting to realize that there are other options. Of course, human inspection is not ideal for obvious reasons and definitely poses speed and repeatability problems for production inspection. For example, the display in the lower left, how many human inspectors might miss the MURA defect when inspecting at speed? Traditional machine vision has also been applied for defect detection displays, but there are metrological downsides. These systems don't capture photometric values and lack algorithms developed around human vision, which can lead to inconsistencies. Without metrology, defect detection ends up being consuming and error-prone. In regard to pixel level uniformity for displays like OLED or micro LEDs, as I've mentioned already, testing relies on robust pixel level measurement methods. The goal is to maximize the amount of detail we capture per pixel. Microscopes are often used in labs for pixel level characterization. A microscope connected to an imaging system maximizes the details by applying full image sensor resolution to fewer pixels so we can clearly see the pixels up close. In a similar sense, capturing a display across several images applies imaging resolutions to each section. The downside is that we don't capture all of the data in a display at once. Using multiple images may introduce error. In either case, full display measurement is time-consuming and sometimes not repeatable. Traditional systems for view angle measurement apply rotation to position at the photodetector and display a range of angles relative to one another. Here we have two examples: a fixture where the photodetector is rotated around the display, and a 2-axis goniometer, which rotates the display relative to the detector. Either method captures very comprehensive data, but setup time, equipment size, and complexity can be high. Maybe this is okay for a lab and R&D applications where we're not so concerned with time or how much data we're acquiring, but we need more efficient solutions for inline, for sure. While lab technology has given us the data we need and baseline test methods to target for inline quality control, production demands continue to increase beyond the capability of what we think of traditional metrology systems. Just to consider how the global display market is set to increase over 50% from 2020 to 2025. 500 million PCs and tablets were sold last year alone, and the billions of smartphones sold each year continues to increase. By 2025, we'll probably be producing around 3,000 smartphones per minute, which is insane. The competition in this industry puts pressure on brands and manufacturers to make better devices every year. So the rapid adoption of automation systems is something that is clearly at the forefront of everyone's mind. The automation market is projected to increase around $60 billion by 2025. These connected factories help manufacturers do much more while reducing the effort and investment. New display technologies are also shaping the future of production. Resolutions and PPI are going way up for both large and small displays. We see pixel size shrinking. For display metrology, this means harder to measure pixels. And when we're measuring and manufacturing more advanced display products like OLED, mini LED, micro LED, and other emissive displays, this means more variable pixels and greater risks of imperfection. We're constantly coming up against increasing demands for production output, and displays are becoming harder to test. So what's the ideal solution for production? And how do the current methods, I should say, really stack up? The ideal production display test solution sort of needs the following capabilities: to understand visual quality, to meet compliance with various standards, ensure high levels of repeatability. It must be efficient for tack times. And that, is including speed, time, space, cost, waste from an efficiency perspective as well. It needs to be integrated into a larger perspective. So always sort of being integrated into an end-of-line fixture, and it needs to offer end-to-end support. But what we've seen, not all inspection systems are equally capable of all of these categories. The spectrum of test equipment extends from the lab to the production line. We see the challenge of inline inspection tackled from both ends. On one end, we see highly scientific display metrology systems like spot meters and spectroradiometers that capture standard CIU measurement values of light and luminance, chromaticity, spectrum, really all the key metrics for understanding the visual quality of a display. On the other hand, though, we have imaging systems like imaging colorimeters and machine vision cameras. Imaging is extremely useful for display testing because it can capture all the areas of the display at once to really understand the contextual information being output. Without imaging, it becomes difficult to measure uniformity or changes in brightness and color across the entire display. It also makes it virtually impossible to ensure we capture all defects that may be present in the display area. Depending on the imaging system's resolution, we could capture several tens of millions of data points at once to compare and look at defect anomalies. Machine vision is a classic imaging system for inline inspection, of course, with speed and defect detection that make it attractive for production testing. But there is one huge key limitation. Traditional machine vision does not apply the principles of display metrology that we've discussed so far. We need the CIE measurement values captured by lab-based systems to get accurate values of brightness and color for display qualification. And the display industry is looking for this more and more all the time. Any system that doesn't leverage these functions can't really tell us the true quality of the display. So how do imaging systems capture relevant metrological values? Well, let's take a look at a few imaging systems in order to understand their capabilities. The key difference comes down to color filter technology and calibrations. Filters regulate wavelength of light received by the imaging system's internal sensor, while calibrations align the system's response to light received by the sensor according to a standard model. A traditional machine vision system is radiometric, shown here on the left. Radiometric systems can measure light, but measurements are unfiltered and uncalibrated. What we get is absolute light power. Unlike a photometric system, these measurements aren't limited by the response curves of the human perception. Typical radiometric machine vision relies on contrast of elements in black and white images to see shapes and detect defects. In display testing, machine vision can detect variations that could indicate quality issues. But without relevant metrological values, the severity of these defects is difficult to completely understand. So next up, we have an imaging system with a color filter in front of the image sensor. In this case, we're showing a Bayer pattern color filter with red, green, and blue filters. This is our typical color vision system. Colored images are helpful because they provide another quality for image analysis, but without calibration, these systems can really only measure a categorical color difference, for instance, the difference between maybe red or blue. These systems can't measure an absolute quantifiable value, and they don't take into account how each color is perceived. In order to do this, an imaging system must apply a calibration, which tells the system how to align its response to light according to a standard, such as CIE color matching functions. Now, with a color filter and calibration applied, we have a system that can give us relevant measurement values to quantify any visual quality based on the luminance and chromaticity. So why don't machine vision systems fit the bill? Looking at traditional machine vision cameras, most are radiometric and incapable of color measurement. Of those that use some kind of color filter method, they're using a Bayer pattern filter like the one we saw on the previous slide. Technically, Bayer pattern machine vision cameras can be calibrated to match the response to light and color to CIE functions. However, there are a couple problems. For one, out-of-the-box machine vision camera is not going to have the calibrations built in, and it will take a lot of time and effort to create a custom calibration to ensure alignment with CIE. The second problem is represented on this slide. The innate spectral response of an imaging system varies wildly based on the different color filter methods. A Bayer pattern filter offers nowhere near the spectral response we need out of the box. So in other words, the calibrations that are required before are not properly applied. The way the filter weighs wavelength of light is extremely divergent from CIE color matching functions. Another color filter method is designed with CIE functions in mind. This is called a tristimulus filter system because it applies color filters for the tristimulus values of cap X, cap Y, and cap C. Out of the box, a tristimulus imaging system is almost right in line with CIE functions, even before calibration. The importance of this difference can be relatively small when measuring highly uniform displays. As long as you calibrate your imaging system, the color filter method doesn't matter much. But if a display's output starts to change from the initial calibration point, let's say, for instance, a non-uniform color, the Bayer pattern system's accuracy will drop greatly and not provide you with the right level of color analysis. The accuracy ranges of each method are illustrated in the chromaticity diagram on the right. These risks, plus the amount of custom work to get a machine vision system calibrated in the first place, really rule out machine vision as a display measurement device. Despite its production advantages, machine vision lacks too much of the metrology side. So back to the drawing board. Here we need a metrology system that accurately can qualify displays. So we need a lab system, right? Well, yes and no. As we've seen, lab systems don't meet many of the demands of production inspection. Really, neither machine vision nor traditional metrology equipment provides an appropriate solution for inline display testing. This is where a lot of manufacturers feel like they're stuck between a rock and a hard place, often maybe having to try and implement multiple pieces of technology to really achieve what they're looking for. Discrepancies among optical inspection technology can lead to common misconceptions about the ability to apply true metrology systems in a production environment. As an example, we can't get all of the data or capability we need for inspecting the line. Lab equipment supplies the most complete and accurate spectral, photometric, and colorimetric data, but the lab equipment is too bulky, large, complex, or time-intensive. We have to make a sacrifice between resolution and speed. So as an example, you may need resolution to pick out tiny details in a display, but high-resolution inspection takes longer to process. We can't get a system that meets our exact requirements because, as an example, there's really not a lot out of the box that requires not a lot of time to configure. We see a lot of solutions, but they're not highly customizable, or the solutions are far too costly. Metrology software isn't built for fully automated inline inspection like machine vision software. Inline inspection needs rapid pass-fail data based on a series of inspection runs without manual intervention. And of course, one of the last thoughts is we need a system that connects production to the rest of our ecosystem. So it needs to communicate with our fixtures, our robots, etc. But the metrology systems don't really offer the same kind of API and programming languages that machine visions do. Between highly accurate metrology and production inspection systems, it seems like there's a gap here, as you can see in the slide. But actually, there is a way that we can get both. This is a gap that Radian fills with our technology. Our expertise balances metrology and production. We've been metrology experts for over 30 years now, and we've developed our systems to meet the efficiency goals from the beginning, starting with the very first application of imaging for photometric measurements. The point is, we develop metrology systems specifically to meet production goals. This is where I'd like to show you how we debunk the common misconceptions that I've already gone through in this presentation. So let's take a look at some of the systems and technology advantages that we've designed specifically to address the production concerns. Radian is equally focused on getting the right data as enabling production or operations, but we do start with the baseline of accurate data. That's because quality expectations can only be met by evaluating visual properties of the display in scientific values. The misconception that scientific lab equipment can only be applied in the lab is countered by Radian's fast, compact, production-ready imaging colorimeters. All components of the imaging system, that be its lenses, the software, are developed together to provide an all-in-one system that brings lab-level capabilities to the production line. Here's a Prometric imaging colorimeter, which applies imaging like a machine vision system would, captures extremely accurate CIE matched values for luminance and chromaticity, and provides defect detection like Mura, dead pixels, and much more. The system is purpose-built for production. Following this, we have our Prometric Isc, which combines the capabilities of our inline imaging colorimeter with an integrated spectroradiometer, adding CCT, CRI, white point, and more to the list of measurement capabilities. Radiant has camera and lens combinations that are packaged together that offer capabilities that are much larger than what lab systems had previously been able to do, and we bring that capability onto the line. As one example, our Conoscope lens shows here a measurement solution where we can look at the viewing angle performance of a display, but we can do this instantly with a single image acquisition at a single point to understand things like plus or minus 70 degrees of the angular distribution for luminance and color. This is a huge time-saving solution compared to a goniometric system that might have been used in the lab. The resolution of inspection systems is a key specification, especially with shrinking pixel sizes of today's displays. Radiant has long provided the highest resolution imaging metrology systems and continues to optimize our systems for high resolution that doesn't sacrifice imaging performance. Most inspection systems offer around a 12 megapixel resolution or less. At Radiant, we offer 61 megapixels and beyond today. As an example of this difference, we're showing two images here of the same display with several defects. As we process the image with our high resolution system, we can start to pick out these defects using luminance and contrast thresholds. An analysis identifies all defects far beyond the detection capabilities of machine vision and even sometimes our own eyes. Resolution is really key when it comes to pixel level measurements for today's emissive displays. So we got to think of covering all of our bases. Here are the measurement images from Radiant's high resolution systems. We're measuring an OLED smartwatch, capturing the entire display in a single image while still maintaining sufficient resolution per display pixel for accurate brightness and color measurements. The ability to apply this level of resolution itself is an advantage in regards to speed. We have an instant analysis with no loss of data and zero downtime. No need to spend time setting up and applying a microscope lens or low resolution system to capture multiple images of the display. The resolution here allows us to get so much detail of each pixel in the image. Actually, in fact, we can derive a measurement from over 100 sensor pixels covering the area of a single display subpixel. Applying higher resolution to capture an image of display means much more data must be processed and output. We need to make sure that this doesn't slow down the inspection though. So what are the potential trade-offs? The misconception that you have to make a huge sacrifice in one direction or the other, either resolution or speed, it's just not true when it comes to optimized systems that are designed for this type of application. At Radiant, one of our top priorities is to meet the minimum measurement times that are consistent across high resolution systems. We do this not only by optimizing our internal imaging components, but by upgrading our data output processing and communication to meet consistent benchmarks. Using GigE and 10 GigE connectivity allows us to send millions of pixels worth of data to a PC instantly. We've also moved from CPU to GPU processing, which provides hundreds more of cores for running concurrent data, supporting image processing, analysis, asynchronous software functions. This is really ideal for speed because by running one step of our inspection while performing multiple other aspects, we've been able to use GPU processing to reduce our takt time by more than an order of magnitude, which has been completely game-changing in the production line environment for our consumers today. In this table, we're showing different resolutions of our Prometric imaging colorimeter. As resolution goes up, connectivity and processing allows us to maintain our speed advantage. Even the 8 megapixel camera is only slightly faster than our 61 megapixel today. Now, there's a key difference between metrology systems designed for production lines and metrology systems designed for your production line. No one's inspection needs are exactly the same, and no one AOI system fits the exact requirements really out of the box. Often, we see manufacturers are left to customize their own equipment and software for unique specifications, standards, and various types of integration. The misconception that deploying the right AOI solution for your needs means doing a bunch of arduous, costly legwork is countered by Radiant's approach to the market. Radiant develops solutions to meet real inspection requirements. This means consulting with you first and foremost, getting to understand your objective, and of course, implementing those objectives for your production environment. From here, the process is really a collaboration. We work together to develop a solution toward the same goal. For fixturing needs, Radiant partners and works directly with a number of highly qualified integrators around the world. We also have in-house development teams who adapt software for your application. Maybe you need some analysis functions that other customers we work with do not. Being a hardware and a software company allows us to offer that level of flexibility that no one really on the market can offer today. The Radiant dev team has created many flavors of our baseline TrueTest software to support projects all over the industry. And we have a long history of building custom device interfaces, enabling direct communication between our equipment and any device you may be testing. As an example, much of our optical development is the result of configuring technology to address specific customer needs. Radiant's XRE lens was designed to enable display testing within the unique physical parameters and viewing conditions of AR, VR, and MR headsets, which are becoming widely popular in the market and are only set to grow further in the future. Headsets are becoming so diverse in their specifications, their form factor, and just how they sort of adjust to the head themselves, that different types of inspections are needed. Our lens was designed and features different configurations to allow the imaging system to achieve the viewing position of the human eye inside any headset and any form factor. This allows the system to measure displays as they're actually being seen by the end user. The folded optics not only allow the in-headset measurement while headgear is present, they make it possible to design stereoscopic configurations like the one in the middle here, where both the left eye and right eye position are measured at once. In terms of automated inspection software, machine vision has set the bar: fast, continuous inspection, pass-fail output, universal communication, of course, but it doesn't capture light and color values that we need. Typical metrology software is excellent at this, but lacks automation benefits, as we've talked about before. Of course, this is a misconception that you can't have metrology software with automated inspection capabilities is completely thrown out by Radiant's TrueTest software, which is a purpose-built solution. TrueTest was made to be an automation engine for metrology applications. The interface controls all elements of the inspection, pushing test images to displays, initiating the camera and lens functions, and of course, outputting the data. Like traditional machine vision software, TrueTest is a toolbox of inspections: registration, defect detection, dimensional measurements, plus any analysis, capture, or evaluation of photometric, luminance, chromaticity, uniformity, and more can be achieved. A TrueTest sequence runs several tests in succession to evaluate a display for any number of visual qualities. TrueTest runs asynchronously, which means processes are happening in parallel to optimize the measurement time. As an analysis runs, the system continues to capture and process subsequent images, cascading down the test sequence. Multiple step sequences runs continuously and provide pass-fail results based on user-defined tolerances for defect and measurement values. Here's a quick look at TrueTest's analysis sequencer running several display tests in series over a course of a few seconds. In each step, the software is sending an image to the display under test, triggering the imaging system to capture the display, and beginning the image processing and analysis. You can almost visualize how TrueTest is starting to capture the process of the image for a new test as it's asynchronously running, and the analysis for the last image at the same time is being processed. We mentioned another benefit of machine vision. They are great for interfacing with other equipment. Metrology equipment developed for the lab doesn't really need that kind of integration capability. An operator provides the commands, the data is output to a connected PC, and honestly, for that reason, today's inline metrology systems typically don't have the kind of interface capability needed to connect to larger manufacturing ecosystems. The misconception that there is no metrology software with integration capability, again, is wiped out by TrueTest. TrueTest was developed to be the production inspection platform. We know data has to be exchanged between multiple separate pieces of equipment to meet the greater automation goals, from robotics to PLCs to overall output platforms. TrueTest offers built-in APIs, SDKs supporting languages like LabVIEW, Python, .NET, C#, with a variety of different PLC device interfaces, things like Allen Bradley, Omron, Siemens, and so much more. In a recent project, we worked with one of our partners, CP Industries, who designs fully integrated systems for evaluating windshields for head-up displays. They also do quite a few other things as well. Their story began many years ago with machine vision, though. Using traditional vision systems in their fixtures, CP tried to capture the data they needed to meet strict measurement standards from their customers. The number of calculations they needed was massive. They were having to do a huge amount of custom programming to get the machine vision system to capture the appropriate information and, of course, ensure the software output was relevant. Radian was able to replace both the camera and the software components with a photometric system. Not only would the photometric values address many of their testing requirements, our software algorithms were already built to do the kind of testing they needed. The rest of the development work to meet the specific requirement was handled directly by Radian. And as we see in this video, CP applies robotics for positional measurements. Our camera integrates easily with this equipment, and we were able to apply API communication to all aspects of the system. Here, software synchronizes all measurement positions, camera functions, and testing with robotics to output rapid pass-fail data. I'd like to mention just one final advantage Radian has to offer for production display testing. Although there's no misconception that you should have support for your production inspection system, Radian is able to support production operations directly at the global scale. We have over 70 application engineers working directly on projects throughout North America, China, Taiwan, Korea, Japan, and Vietnam. We provide local integration, training, validation, customization, equipment maintenance for calibration, technical support from our direct regional offices, which are found in Asia, North America, and Europe as well. In addition to our primary manufacturing at our headquarters in Washington State, we just recently opened our first China production facility in Suzhou, so we can support projects in China and the greater Asia Pacific with new equipment and maintenance as immediately as possible. Radian really does aspire to be a leader in the production display industry. And before we wrap up, I'd like to summarize the solutions we have to offer that bring metrology to any production environment. At Radian, at Radian, Solution is a unique display test system designed around your requirements, but based on the same Prometric and TrueTest platform. Camera, lens, and software come together to form the ultimate combination of scientific metrology and machine vision efficiency for display testing, so we can check all the boxes for your production inspection projects. These are some possible combinations, including solutions for general display, augmented reality, virtual reality, head-up displays, and much more. We also offer systems to put more metrology power on the line. I want to spotlight this system because it effectively brings two high-performance display metrology systems together and equips them for an inline measurement solution. Our Prometric Isc Solution is a combination imaging colorimeter and spectroradiometer. With this system, we get the same advantages of Radian's Prometric imaging colorimeter with high resolution, high speed, fully automated inspection capability, and industrial communications. But we also get so much more. We get the ability to capture the spectral and spatial measurement data simultaneously using a single device. And this means no need to apply imaging systems and spectroradiometers separately inside the fixture or end-of-line platform, and we can derive additional measurements from spectral data like CCT and CRI. We also can apply calibrations in real time during the measurement, and this means no downtime to swap around equipment, positioning a spot meter to gather spectral data, calibrating the imaging system, and then moving the spot meter position or the imaging system to a different reference point. Not only is this faster, inline calibrations ensure repeatable CIE-matched color measurements. It also ensures continuous inspection for fully automated testing without manual intervention, which is probably one of the most important aspects. So to wrap up, as we've seen, the principles that govern display metrology are intended to provide a very accurate scientific approach to quantifying the display's output. Because of this, scientific systems were originally engineered to capture metrology values designed for lab environments where measurement time and space are flexible. However, that means traditional display measurement systems lack efficiency, communication, automation, other ideal characteristics for production line inspection. On the other hand, production inspection systems like machine vision were not designed with display metrology in mind. They are fast and efficient, but they simply don't capture the measurement data required to understand the display output. At Radiant, we start with the metrology requirement and continue to reimagine metrology solutions for unique measurement scenarios. For decades, we've optimized the lab measurement systems to meet production demands, with currently thousands of systems testing millions of displays every year in production lines around the world. So as we get into our Q&A, if you need to sign off, I definitely appreciate your time today, and I apologize for the way I might have sounded. If you have any questions, definitely feel free to reach out to me directly or to us at info@radiantvs.com. For those of you staying on, you can ask any questions. I'd be happy to address them, and I'll let the moderator take over from here. Appreciate everyone's time.
Amazing. Thank you so much, Matt. I think everyone would agree, very information dense and super in-depth look at Radiant's AOI systems and technology. I think without further ado, we'll launch into some of the questions that we have. Some great questions here. So I'll just publish the first one. This comes, so in terms of looking at specifically the CIE diagrams that you mentioned, what CIE diagram in terms of year and type perhaps would you say is the best for evaluating colors from displays given a modern spectrometer for measurements?
Yeah, so as I mentioned in my presentation, there are two types of CIE charts, the 1931 and the 1976. To be honest, if we look at the consumer electronics industry, the automotive industry, the medical industry, most of them are using 1931 and focusing on what we call CX and CY. In the U prime V prime space, so the 1976 space, we still see that being governed by some military applications and some aerospace, but the more common one for sure is the 1931 CIE space.
Okay, very interesting. Sorry, I just had to unmute myself there. The second question coming in is one regarding what is the maximum viewing angle of the Conoscope and the working distance of that tool as well?
Yeah, that's great. So we actually have a couple different conoscopic measurement solutions depending on your application. But if we focus on what we call the visible conoscope, that offers plus or minus 70 degrees of evaluation. And the working distance is 3 millimeters from the display. And we look at a minimum size of approximately 10 millimeters in diameter.
Okay. What's the brightest resolution image that can actually be captured on the line?
Oh, that's a great question. So we use high dynamic range imaging solutions coupled with a technology called electronic bracketing, which allows us to expand our fundamental range through exposure sets. We can measure greater than 1 million candela per meter squared by applying the right neutral density filter in front of the sensor, and of course, using the right exposure brackets. And these are all things that Radiant can support and evaluate with the end user to understand what their overall needs are. One of the things I didn't highlight is in our I-series imaging colorimeter, we actually have a built-in neutral density filter wheel. And this neutral density filter wheel can automatically apply the right ND filter, ND1, 2, 3, or above, to ensure that we get the appropriate dynamic range necessary for measuring extremely bright light.
Okay, amazing. Yeah, sorry, just got one more question here. No, a few actually, if that's all right.
Yeah, for sure.
In terms of the software that you actually use, you say it's asynchronous. How does that work? Sorry.
Yeah, so what's really nice about an asynchronous software is that we can compute multiple algorithms simultaneously. So an example would be we capture an image of a display. Let's say it's on a robotic arm, and we want to move the robotic arm to 5 different positions. We can take a measurement at one position and maybe run 5 different types of analysis. So we can measure the white uniformity, we can look for stuck-on pixels, we can look at the color uniformity. And as we acquire that image, we can move the robot to a different position, maybe a different viewing angle position or a different eye box if we're talking about like a head-up display technology. And as the camera is moved from position to position, the software is still running. What's nice is for one acquisition, we could run 10 different types of analysis. If we were looking for pixel defects, line defects, Mura, all of that can be computed simultaneously through the asynchronous mode, which reduces the general tack time by several orders of magnitude compared to traditional vision systems or softwares.
Okay, wow, okay. How do you define the radiance and or the luminance of a fully resolved pixel in that line?
Yeah, so that's an interesting question. So of course, when we want to understand the luminance of a fully resolved pixel, we want to ensure that we have enough sensor pixels over that illuminating display pixel. And generally speaking, we like to run a sort of standard gamut where we want at least 5 pixels if we're looking at luminance, and we want at least 10 sensor pixels if we're looking at color, as an example of an emitting display's individual pixel. And the same thing for radiance. Okay.
That's how angular dependent are your imaging photometers when measuring that luminance and or color for display?
Yeah, that's a question that people ask us all the time. And that's a really great question, because many people probably don't know that we go through something called a linearity scaling calibration and a flat field calibration. Both of these calibrations help us with the orientation of the camera and the angular dependencies of the device under test back to the camera lens and the sensor itself to help mitigate the angular degradation that many people might see with uncalibrated systems. We also have a variety of different types of ways to sort of evaluate what that angular fall off or what that dependency might be for a lighter color perspective from the angular output. And we can calculate whether we need to look at an increased working distance to fundamentally cut down that angular dependency. So by calibrating our lenses, having a variety of different lenses, applying mathematical calculations to understand working distances, we can ensure that we can meet a variety of different requirements and accuracy specifications without, worrying about huge drop-offs in luminance or color dependencies based on angle to the sensor.
How accurate are those systems at measuring displays with non-uniform color or non-uniform brightness outputs?
Yeah, so the specifications of the device are, we look at accuracy outputs of plus or minus 3% for luminance and 0.003 for CXCY chromaticity values. So very small shifts in the display can be accurately detected and characterized.
In terms of the, what was the largest FOV in resolution for that defectivity inspection system? The question specifically actually relates to 6, 8, even 12-inch wafer level detectivity inspection for HVM. Sorry if I phrased that poorly.
Yeah, sure. So we have a variety of different lens options. So if we're looking at like 6, 8, and 12-inch sort of wafers, we have lensing solutions to accommodate all of those, from microscope objective lenses to narrow field of view lenses. We have things at 24, 35, 50, 100, 200 and above, plus specifically designed microscope objective lenses to help with that as well. So we do a lot of wafer level testing for micro LEDs, micro OLEDs today, as well as traditional LED technologies. So lots of options there.
Amazing. This next question is quite dense, quite it looks like a lot to unpack as well. A question asking, do you need chromaticity information for Demura? Again, pronunciation, but Demura, or is luminance sufficient? Is it corrected for both color and intensity on the pixel level?
It's a great question. So traditionally speaking, Demura has been done with a photometric camera, so what we call a photometer, which doesn't necessarily rely on the color component. We can adjust it from the luminance channel itself. However, as display technologies are changing, we do have customers who are now working with us on color Demura. So I would say if we were to go back a few years ago, we were primarily focused on the photometric side in correcting demura on the Luminance channel. However, with the changes in display technologies and the advances that are being made, we are also evaluating color demura as well.
Amazing. Just a couple more questions, and then we'll draw it to a close. But would this question comes: would Radiant help customize mirror detection specifically for mirror detection specification for our application? Obviously, I don't know what that application is, but specifically detecting non-uniform gradient. What parameters do you think you'd set? Come across?
So whenever we sell our technology to any customer, any market, any industry, it's a really collaborative consultant sort of approach where we come in, we educate, we train the team on how to utilize our software, if that's something that they wish to have control of. Otherwise, we have teams that come in, our application engineering team, our software team, the sales team themselves will come in, look at the display technology, look at the areas of concern, and we can go through and work and configure the algorithms to meet the specific analysis requirements that the customers have. It really is a collaborative approach. We don't just sell cameras or software and say, run off and do your thing. It's a partnership once we start working with someone to ensure that they're successful. So for sure, we would definitely work with whoever asked that question to come on site and evaluate their technology.
Amazing. Final question for you. Partially save your voice, as I know you're dealing with illness at the moment, but how does mirror algorithm align to human vision if people can't necessarily detect the issue itself?
Oh yeah, that's a great question. So we use a variety of different analyses inside our mirror algorithms. But as I talked about in my presentation, one of the key fundamentals is the just noticeable difference, so JND, which basically we're looking at how the human visual response to the display or the defect is perceived and what the contrast sort of fall off is. One of the things, if a human eye cannot detect it, generally speaking, the camera might find what we call like false negatives. So we would threshold out that detail if it's not actually apparent. So we don't want to be finding things that the human eye can't see at all. Obviously, we would deem those as not real defects. If we can't see them, how do we know that they're true? So the idea behind our technology is to replicate human vision in an accurate and repeatable way, and to set the appropriate levels of thresholds and adjust our algorithms to define the smallest level defect that the human eye can perceive, but not to find things that are invisible to our eyes.
Oh, okay. Okay, well, thank you so much for that. I think we're gonna call it there. That was very informative, Matt. Thank you so much. Your voice sounded great, so you don't need to worry about that. Any questions that weren't answered? I know there are a lot of very, very in-depth, very interesting questions as well. So thank you to all our audience for that. They will be answered after the fact by Matt and the Radiant team. So we've got an archive of them. We'll get around to that as well. But thank you so much to Matt, and thank you to everyone who attended. Really good webinar. So thank you all.
Yeah, thanks everyone. If anyone wants to reach out to me directly, you can see my email address is up there, matt.scholz@radiantvs.com, and I'd be happy to answer any of your questions, or feel free to reach out and I can set up a call with you as well. Appreciate everyone's time. Have a great afternoon or morning or evening.